Hello, welcome to the presentation of this project, Dice Results Checker for ECE140, Dr. Z's class. Team members are Cameron Hurst and myself, Antonio Robledo. The narration for this video will be done by myself. Cameron is indisposed at the moment, but she worked very hard on this project alongside with myself. So, if it's okay with you, it'll just be me. So the purpose of our project is we wanted to make something that was a state machine. A lot of people in the class were talking about doing either ALU or a multiplier, and we wanted to incorporate some of the ideas of combining CMOSs in such a way that they did something, I want to say, not more meaningful, but just something different. And also getting the state machine to work, we knew when we discussed it that it could be a challenge, and it was a challenge, but we feel like it was a rewarding challenge because we got to learn the software a lot more intricately than maybe our classmates did, and that our end results we were very happy with, and all along, what makes a successful project is that it works. We had fun doing it, and we learned a lot. So off to Electric to show off the project a little bit. Just starting a little bit with the lower design, we built our project in such a way, as you can see here, we built it from the lowest level, which we called our level 5. And then we built upon those levels until we got to the number 1, as you can see here, which is the overall. So the backbone, probably of the entire project, which is I would say in most CMOS design, is our NAND gate. So here's our schematic of our NAND gate, and here's the layout of our NAND gate. And in higher levels, that this CMOS gate right here, this primitive, it's the backbone of everything. Okay, so which led to the way we made our NORs, our XORs. We made our XORs using NAND gates because we wanted to keep the design consistent. And as far as XOR design, this was in our opinion, one that looked the most elegant. And as you can see here, we used our higher level. Let me open one of these up. We built this using the lower to upper level design concepts that we learned in class. Like, this is what VLSI is about. We went from building one NAND gate to then using those to make an XOR gate. As you can see, connected all these with two metals. We had a common VCC and a common ground for all those. And the XOR is used in a lot of different ones. For example, if we go up another level, we'll see here the 1-bit adder. And the 1-bit adder was created by 2 XORs and 3 NAND gates. Then if we open these up, you can see the same design, very consistent throughout. And then using the same design, going from a 1-bit adder, we made a 4-bit adder, which looks like this, where we have our inputs A and B, we have our carry in, which is not used in the first bit. This is from top to bottom. We go with the least significant bit to the most significant bit. As you can see, with the first bit, you don't need a carry in because there's nothing to carry in. And here on the C out, we carry out, and we have it connected all the way down here to the carry-in of this, and so on and so forth, and that's how we built our 4-bit adder. And then if we want to simulate it a little bit here. Okay, so as you can see here, all our A through A3, our 4-bit inputs for B and A, they're all low. Right here we have our delay for the setup, because it's propagating the zeros at start because we don't have any latches on our output. But if I add 1 and ground that, when I add 1 and 1, our S1 should go up, and it did. So this 4-bit adder is working as designed. And our overall, we have here our 4-bit adder, and that's the initial dice roll. And up here we have our inverter buffer bank, which makes sure that it doesn't proceed to the next state in the state machine. Which, before I get into the specifics of how our circuit works, I can show you here that these are the states that we are trying to accomplish. Wherein our first roll is going to get us to the win state if we roll a 7 or 11. However, if we do not roll a 7 or an 11, there is no way to get to the lose state from the first roll. So don't fret. We can't lose. We can only win or continue to play. However, like as I just said, if we do not roll 7 or 11, then we get to this state, which theoretically we could be at infinitely. It's very unlikely, but we could be here infinitely, which is fine. That's part of the game. So going back here to the schematic, here we have our register, our 4-bit register, where we store our first roll. And we keep checking every roll n+1 to our first roll. And then if that roll is the same as our first roll, as you can see here, then we win. But if we ever do that, then roll a 7 or 11, then we lose. So that's the only way to lose. If you roll a 7 or an 11 after your first roll, before you match the initial roll. So after going through the layout a little bit, I can then show you the results of rolling a 7. So here we have a 1 and a 2, which means we're inputting a 3 at the A's. And on the B's, we're going to input a 4. So we're adding 3 plus 4. As you can see here, S0 is 1, S2 is 1, S3 is 1, and S4 is low. So 0, 1, 1, 1 is 7. So that should mean that we won the game. So now all we have to do is get past the delay of the inverter bank, check the roll, and as you can see, ta-da, we won. We successfully won a game by rolling a 7. So that is how the state machine works. And this here is a comparator. This is where the comparator goes. So after the delays from the roll get enabled, the registers have latches inside of them that'll output towards the comparators, which will let you know what state you're on, should you input a re-roll, and so on and so forth. Dr. Z, Cami, and I enjoyed the class immensely. We won't be able to have the opportunity or the privilege to take another one of your courses, but we learned a lot from you, and we appreciate everything you taught us.